Alright guys, so yesterday we were taking a look at specifically the square root graph and how we can move it left, right, up, down. Maybe we want to flip it, maybe we want to stretch it, okay, and how all those different transformations were related to the actual equation of the square root we were given. I know we were on page 30 yesterday and we finished it up, but when I went back and looked at it, I forgot to mention one thing. Okay, so we're going to look at the last two graphs that we finished with yesterday, and then we'll take a look at some other things about this section. Hey Maddie, they want to see you in the office just for a second, okay? You can leave your stuff. Well, actually, do you want to take your stuff with you, just in case? Okay. All right, so if you take a look at the bottom, the directions said, based on your observations, predict how each graph of the function would be different from the original parent function we started with, state the changes, and then graph it. And we did all that yesterday. Okay, we identified all the different shifts and movements. But the last sentence says, state the domain and range. Good morning. Anything for the office today? I think we're good. Happy Friday. All right, so based off of our transformed graphs from yesterday, okay, they're on the board, we're going to state the domain and range of each of these. Are we familiar with those two vocab words? Domain, range, have we heard of those before? Maybe? Yeah, Rebecca? Okay, so domain are x values and range are y values. Specifically, the x values on the graph where you have a curve or a line or whatever the picture is. And then the same thing for the y values, wherever your curve or picture is located. So if you take a look at the first one, typically for domain and range, well, there's different ways you can write it, but it's most commonly used in interval notation. So we're going to try to figure out what is the smallest x value that this graph would go to, what's the highest x value that this graph would go to. So if you can imagine, because we got to be careful, there's an arrow pointing to the left, how far to the left would that graph actually go? Can you think about the smallest x value that it would reach if it's going to go forever to the left? -10, -100, -1,000,000. If it's going to go forever and ever, what do you think it's going to go to? Negative infinity, right? Okay, so if it's going to go forever to the left, the smallest x value we'll say is negative infinity. What's the furthest to the right that your square root graph goes in terms of the x values? Does it reach an x value of 5? What do you think, Rebecca? 1. Notice how this ending point we have is at the x value of 1, and immediately after that we no longer have a graph. So the furthest left it goes is negative infinity, the furthest right it goes is a positive 1. Okay, we're looking for the furthest left point and the furthest right point. We'll eventually talk about, well, what if we have some breaks or things within the graph, but we'll get to that later in this section, okay, and how that changes the domain. Let me ask you this. Will you ever reach negative infinity? Will your graph ever actually get there and stop? No. Okay, so if your graph never actually reaches that point, we show that idea with a parenthesis. Okay, it means you will not reach that particular location. Does your graph ever reach or touch the x value of 1? You see how that's different? Okay, so if your graph touches that point, we use a bracket. We're definitely going to look at more domain and range in this section. This is just kind of a little intro. Maybe you've seen this before, maybe you haven't. Okay, so that's the furthest left x value and the furthest right x value. We're going to do the same thing, but now for the y's. Okay, so take a look at your graph. What's the smallest y value for the graph? What's the highest y value for the graph? Can we find those points? Yeah. All right, so -3 is the smallest y value. Does the graph touch that y value? Do you actually have a point there? Will you reach it? Yeah, so we have a bracket. And then what about the highest y value? Yeah. Infinity. Okay, we do have an arrow, right? And if you were to trace this graph, wouldn't your finger continue to go up, right? Forever and ever? So the highest y value would be infinity. Will you ever reach infinity? No. So we have a parenthesis. All right. Can you guys try the next one for domain and range? Furthest left, furthest right, furthest down, furthest up. And then check out if you need a bracket or a parenthesis. Any takers? Either one? Domain? Range? What do you think, Rachel?
For domain would be the smallest would be 0.
Okay.
And the largest would be infinity.
Okay, I like the infinity. This starting point right here has the x value of 1. If it was 0, it would go through that origin. Do you see that? Okay, so it should be a 1 instead of infinity. Okay, but you were very close. Notice how you touch 1, so we would have a bracket there, but you'll never reach infinity, so there's a parenthesis. What about the range? Lowest y value to highest y value? Go, Tori. -infinity to 5. I like it. This arrow, if you were to trace the graph, would continue down, right, forever. So that would be a -infinity. The highest it goes is, oh wait, did you say 5?
Yeah.
1, 2, I think it should be 3. A height of 5 is up.
It just looks like a 5.
I know. I know the letter, or not the letters, the numbers might look a little fuzzy, but you might have to like count to get there. Okay, it does look like a 5. All right, so then parenthesis on -infinity and bracket on 3. How do we do? Pretty good? Okay, so let's go ahead and take a look at a few of more of these transformations that we were talking about yesterday. Nice organized table format where we're going to have like a go-to list of everything that we discussed yesterday. So on the left, you have all of these different transformations. Notice how we're adding something, subtracting something. We have this inside idea versus outside idea. We have negatives. We have a multiplication out front. Okay, we're going to nicely organize all these different transformations in this table. So in this first column, we're going to describe the shift or the change or the reflection, whatever it might be, based off of the equation on the left. So notice how you are adding c. We're going to say c is like a number, okay, a constant, any number you want to pick. If you were to add a number on the outside of the equation, how does that change the graph? Can we dig deep from yesterday? If you add a number on the outside, what does that cause your graph to do? Yeah. It shifts up, okay? And specifically, you go up the amount of c, okay, whatever that number is. Like if c was 7, you'd go up 7 spots. Okay? So if that's the transformation that's being done, how does that transformation affect the coordinates of the graph? If you're moving something up, are you affecting an x value or a y value? Can you think about it? Good, Maddie? A y value. Okay, so if you're only moving something up, the x value of the coordinate stays the same, but the y value is changing. Specifically, you're moving it up or you're adding a specific amount to it. So we would be adding that number c, whatever it might be. Okay, so this is the transformation in words, but this is what a transformation might look like in terms of a coordinate, okay, an ordered pair. What if we were to subtract a number on the outside? How does that change your graph? Good, Marie? It would go down that number, yep. Okay, so how would that affect the coordinate, the ordered pair? Yeah.
It would be x and then
Y minus c. Good. All right. What if we add a number on the inside? Do you see how that's inside parentheses? Okay, yesterday we were working with inside square roots, okay, but it could be inside parentheses, inside absolute values, any type of bracket or kind of grouping symbol. What if we were adding on the inside? How does that change the graph? Good, Marie? You would think. Left C, yep. Okay, so you move it left C. How does that affect the coordinate? Are you affecting an x value or a y value if you're moving it left? Yeah. An x value. So would your x value get smaller or bigger if you're moving it to the left? Yeah. Smaller. So we would be subtracting c. Yep. But the y value would stay the same. If you're only moving it left, you're only affecting the x, not the y. What if we subtract c on the inside? Good, Maddie? We got right c. All right, and what about the coordinate? If you only move it right. Yeah.
x plus c and y.
And the y would stay the same. Nice, nice, nice. We're doing good. All right. What if we have a negative on the outside? How does that change the graph? Yeah. The horizontal axis, meaning the x-axis. Good. Okay, so you can say flip. The mathematical word is reflect. Okay, so you're reflecting over the x-axis. Okay, so try to visualize it. Okay, you have a point maybe above the x-axis, and if you reflect it, it would now be below. Okay, are you affecting an x value or a y value if you're flipping it over the x-axis? Maybe I can draw a picture if we're struggling. Yeah. You're affecting the y value. Okay, so graphically, bless you, graphically speaking, if you have a point up there and you reflect it down here, notice how the x value is the same, but the y value changed. How did the y value change? Let's say this y value was 4. If you fold it over, yeah, it changes sign. This would now be -4, right? So the x value stays the same, but the y value switches sign. All right, let's amp it up a bit. Maybe we'll throw in multiple transformations. What if we add c on the inside and we add a different number on the outside? You want to give it a shot, Marie? Go ahead. All right, left C, up D. So now you have two transformations. You got to think about how is that affecting your x coordinate? How is that affecting your y coordinate? What might it look like? Give it a shot, Rebecca.
X minus c
Uh-huh.
and y plus c.
There you go. If you're moving it left, the x value is getting smaller. If you're moving it up, the y value is getting bigger. So we would subtract the c but add the d. We doing okay? All right. Next one, if we subtract C on the inside, subtract D on the outside. Good, Marie? Write C down D. How does that change the ordered pair? Yeah. X plus C, Y minus D. Good. We're kind of going through basically all of the combinations of these. How about the next one? If we add C on the inside, subtract D. Good, Marie? Left C, down D. I think we're on a roll. What about the coordinate? Good, Ashlyn?
X minus C, Y minus D.
Y minus D. Good. And the last one for the inside, outside, minus C plus D. Yeah. Right C up D. How does that change your coordinate? Yeah.
X plus C and Y plus D.
Y plus D. We doing okay? All right. What if we have a negative on the inside? How does that change your graph? Yeah. Okay, so we're going to reflect over the y-axis. If you want to draw a little picture, let's say we have a point in our first quadrant. If we fold it over the y, it's now there. So what's changing? You affecting an x coordinate or a y coordinate? Yeah. The x coordinate. Notice how maybe if this one was 4 and you fold it over the y, it would now be negative 4. So the x value switches sign, but the y value, aka the height, stays the same. Okay, it's kind of opposite of the one we saw before, right? Okay? Alright, next one can be kind of tricky. What if we were to take the absolute value of a graph? What does the absolute value function do? Can you describe it? Yeah?
Well, it's trying to see how far away it is from 0.
Okay, so in terms of a number line, how far away it is from 0, aka a distance, right? Can distance ever be negative? No. Okay, that's why the answer for an absolute value is always positive. So, graphically speaking, if you were to take the absolute value of a graph, you would change any negative point to a positive one. Does that make sense? Okay, so maybe we'll say here any negative point becomes positive. Right? So in terms of our coordinate here, what's another variable we can use instead of f of x? What does it stand for? F of x and blank are the same thing? Yeah. Y. Okay, so in terms of the coordinate, you are changing any negative y value to a positive one. So the x coordinate would stay the same, but the y value is what you'd be changing. Okay, you'd be taking the absolute value of those y's. If I were to try to give you an example, okay, let's say we had, I don't know, we'll do a common line like that. Okay, if I were to take the absolute value of that line, any negative y value would now become positive. Do you notice how in this third quadrant that line is negative, right? The y values are negative. So if all of those y values should become positive, only this section of the graph would become positive. Okay, so you're only changing negative y values to positive ones. Does that make sense in terms of an absolute value? Okay. All right, what about our last one? From yesterday, what did we say happened in terms of the transformation if we multiplied by a number out front? How does that affect your graph? Go, Tori. It's a stretch. Okay, so we have a vertical stretch by this value of A. And if you're vertically stretching it, okay, either making it taller, maybe it's a vertical shrink, okay, maybe you want to make it smaller, that might happen sometimes too. Are you affecting an X value or a Y value? I see the lips saying Y, okay? So the X value is going to stay the same. And how do you think we're affecting the Y value? Yeah. We're going to multiply it by A. Okay, yesterday we saw that doubling idea. We had to multiply all the y's or the heights by 2. Okay, so in this case we'd just be multiplying by A. All right, so there's a nice organized chart for you with all these different transformations that we discussed yesterday. We're going to deal more with the coordinate idea today because all of this we did yesterday. Okay, so let's take a look at the bottom. Yesterday we only covered the square root graph. But hopefully we realize there are other types of graphs out there as well. You have lines, you have parabolas, you have cubics, you have absolute values. And what's nice about all these different transformations is it doesn't matter which graph you have, they all are affected in this same way. Okay, all these transformations apply to any type of graph you have, just not the square root graph. So we're going to go ahead and graph the parent functions of these other types of graphs. That way we can transform them as well. Okay, so what does the parent quadratic function look like? X squared. Can you describe what it looks like or where some points are? Go, Rebecca. 0. Okay, if you plug in 0, you get out 0. Maybe we'll plot some points to see what the shape looks like. If we plug in 1, 1 squared is 1. If we plug in 2, 2 squared is 4. If we plug in 3, 3 squared is 9. Kind of off our graph. What if we throw in some negative numbers? If we square -1, becomes positive, right? And if we square -2, becomes positive. So it looks like we have this U-shaped graph as our parent function. Okay, this is the original. Do you remember what a U-shaped graph is called? There's a name for it. Go, Tori. A parabola. Good. Okay, so if we have a quadratic equation, the parent graph is going to look like a parabola, and then maybe we're adding and subtracting some numbers within that quadratic equation. We're going to shift all of these parabola points based off of those numbers, just like we did yesterday for the square root. Okay, let's go ahead and check out an absolute value. Have we seen an absolute value graph before? Do we know what the general shape looks like? Do we remember? Maybe. Okay, absolute value. Okay, it's going to look like a V. If we plug in some points just to check it out, the absolute value of 0 is 0. The absolute value of 1 is 1. 2 is 2. 3 is 3. But what if we plug in some negative numbers? The absolute value makes them positive, right? So even if we try to plug in -1, we're still going to get out +1. -2 would give us +2. -3 would give us +3. So instead of a U-shaped kind of curved graph, this one is distinctly a V shape. Okay? So this is our parent graph for the absolute value. If we're adding or subtracting some numbers in there, we can shift it depending on where those numbers are found, just like the square root one from yesterday. Okay? Let's take a look at 2 more at the top. Okay, cube root function can be a little tricky. Cubic function, the second one up top, not too bad. That one's a common one. Let's try the cubic or cube root function first. If we were to plug in 0, what number times itself 3 times would give you 0? Yeah, 0. If we plug in 1, what number times itself 3 times would give you 1? Yeah, 1. If we tried to plug in 2, what number times itself 3 times would give you 2? Probably some ugly decimal, right? Okay, if we tried to plug in 3, that would probably be an ugly decimal too. Same with 4, same with 5, yeah. We can do 8, right? 2 times 2 times 2 is 8. So if we were to plug in 8, 1, 2, 3, 4, 5, 6, 7, a little off our graph, if we were to plug in 8, that cube root would give us 2. Let's try some negative numbers. Okay, let's say we plugged in -1. What number times itself 3 times would give you -1? We're specifically doing 3 times because it's a cube root. Yeah, -1. What do you think if we tried to plug in -8? What number times itself 3 times, go Tori? -2. Okay, so the cube root function is kind of this curvy graph on its side. Again, this is the parent function. These are the starting points. If we're adding or subtracting some numbers in different places, we can shift those points. Okay. Let's try a cubic. Okay, if we plug in 0, 0 times 0 times 0, we got 0. If we plug in 1, 1 times 1 times 1 is 1. If we plug in 2, 2 times 2 times 2, we got 8. Little off our graph. If we tried negative numbers, -1 times -1 times -1 is -1. If we tried to plug in -2, -2 times -2 times -2 would give us -8, a little off our graph. Do you see the connection between the cube root and the cubic function? They're basically the same shape, right? Just one's going left and right along the x-axis, and the other one's going up and down across the y. Okay, very similar shapes. So now that we have these other parent functions, we can start to transform them. Okay, and that's what we're going to do with these 4 at the bottom. Okay, so take a look at the original equation you have. What should the parent function look like? We did square roots yesterday, and now we have a plethora of options. We have a parabola, we have a V-shape, we have the cubic, we have the cube root. Which one do you think we're going to use for this first one? Can you tell based off the equation? What do you think, Tori? It's a quadratic because you have the square. So that's telling you that our parent function should be that parabola. Let's go ahead and plot that U-shaped graph. Okay, so the power of 2 is telling you that it's a quadratic. Can we identify any of the transformations? How are we going to shift, move, flip, stretch, whatever, these points? What are the other numbers in that equation telling you? Can we label them? Go ahead, Tori.
Left 2, up 3.
Left 2. And what was the last one?
Down.
Down 3. Okay. What was the order we discussed yesterday? Do you remember? I mean, we only have 2 things we have to do here, but if we have a lot, we got to make sure we do them in order. Remember how we remember? Yeah. RST. Okay, like the alphabet. RST. So, did we label any reflections? No, that's good. Any stretches? No, that's even better, okay? And we do have some translations, though. Left, right, up, down. So, we're going to move all of these parabola points left 2 spots, and then down 3 spots. Left 2, down 3, left 2, down 3, If you want to label that as your final graph, you can. If you're using a pencil, you can erase the parent one because that one no longer means anything. Okay, so the transformations are the same for any type of equation you have. You just have to figure out which equation are you starting with. What's your parent graph? All right, take a look at the next one. What's our parent graph going to look like? Go ahead, Marie. Say it again. A V. Okay, so we have the absolute value bars. So let's go ahead and graph an absolute value shape. We have that V that kind of starts at the origin. All right, so the absolute value bars tell us the shape. What about everything else going on in that equation? Can we identify any transformations? You want to keep going, Marie? Go ahead. Left 1 and up 4. Okay. So far, so good. Let's see one more. Yeah. We got an x-axis reflection. Perfect. All right. RST. We labeled a reflection, right? So all of these points we're going to fold over the x-axis. If you want to label that R, you can. If you're using a pencil, you can erase the parent function. We no longer need it. Did we label any stretches? No. Okay. Laster translations, up, down, left, right. We have 2 of those. So all of these red points, we're going to move left 1 and then up 4. And we'll label that one F. Or if you're using a pencil, you can erase the R graph. We no longer need it. We're starting to see how all this is related. It just depends on the beginning graph, okay, that parent function. All right, let's go ahead and check out the last 2. What's our parent function for the bottom left one? Good, Marie? Cube root, okay. So that's kind of the curved shape on the x-axis. Let's go ahead and identify any transformations. Okay, so the number 3 in that problem, okay, in the equation, is telling you the type of graph. Okay, that's the cube root. But all the other numbers are the transformations. I don't want you to think that that 3 is some type of transformation. It's not an up, down, left, right, flip, stretch. Okay, that 3 is just telling you the shape of your graph because it's a cube root. What about some of all the other numbers and things going on? Marie, I know you're on a roll, but I'm going to give you a break for a second, okay? I know you know what's going on. I got to make sure they know, okay? Any thoughts? Melissa, would you mind giving us one? Good. Reflect Y. Any other takers? Yeah. Down 3. I understand why you said left 2, but...
right 2 because of the negative one, yes.
Okay, so this is the one we got to be tricky. Yes, it normally is left, okay, but from yesterday, that other negative on the inside changes the direction. Okay, got to be a little aware of that, but I understand why she said left. Okay, so let's go ahead and see. We labeled a reflection, that's an R. We're going to flip all of the points over the y-axis. Now notice how this is a little tricky because we have some points on the left-hand side and some points on the right-hand side. If you're folding the points over the y-axis, the left points would be folded to the right and the right points would be folded to the left. So this left point would now be somewhere all the way over here. This left point somewhere to the right. The origin point stays the same. But now the black points on the right hand side are folded to the left. Okay, so if you're starting on the left, you fold them to the right. If you're starting on the right, you fold them to the left. That y-axis reflection. Maybe you want to label that R. Did we label any stretches? No? Okay. But we do have some translations. So all of the red points we're going to move right 2 and then down 3. And we'll label that one as our final. We hang it in there? Do you guys want to try one on your own? See how you do? Okay, check out the last one. You got to figure out what's the parent function and then go ahead and identify all your transformations. Give the graph a shot. Bless you. All right, can we pick out our parent function? Where are the starting points that we need? What does it look like? Good, Rachel? Cubic. And how'd you know that? Good. There's a cube, all right? That power of 3. Good. So the power of 3 is telling you the type of graph. Let's go ahead and start with the cubic. And then everything else in that equation is some type of transformation or change. Okay? What are some transformations you identified? Good, Rachel? Y-axis. Any other ones? Keep going, yeah? Right. There we go. Right 4 and then up 1. Okay, so RST, reflection. We're going to fold everything over the y-axis, so anything on the left is now on the right, and anything on the right is now on the left. So this left point would move to the right, the origin point would stay the same, this right point would now move to the left, and these other ones that are slightly off our graph, they would move appropriately as well. So there's the reflection. So far so good? Okay. Did we label any shifts? Or not shifts, stretches, sorry. No stretches, that's a good thing. Let's now do the transformations. So we said right 4, up 1. Every single point, right 4, up 1, right 4, up 1, right 4, up 1, right 4, up 1. There's our final. Check out. We do okay? Wonderful. Okay. We're going to stop there for today. We're going to do a little bit more next week. Okay, we still are going to bring in those coordinates ideas that we filled out in the chart. I do want to point something out to you though. Okay, for your homework, go ahead and look on page 37. With what we did yesterday and today, you should be able to do this first page. Okay, maybe try to tackle some over the weekend if you can have a free time at some point. Okay. The back, probably not so much, okay, because that's what we're going to check out next week, okay, but I would give this page 37 a shot. See how you do, okay? You guys have a great weekend.